Hello friends, this is Ritu Gupta and in today's session we'll be talking about rational numbers. Let's first try to understand what are rational numbers. Any number which can be represented as quotient of two integers where the denominator is not 0 is called a rational number, or another way of saying it would be any number which can be represented in the form of p by q, where p and q are both integers and q is definitely not equal to 0, is a rational number. They are represented by the capital Q, and the examples of a rational number would be any number like 5 by 12, 2 by 3, and perfect square roots and cube roots like square root of 4 and cube root of 27. All of these are rational numbers. Let us now try to understand the relation of rational numbers with different set of numbers. We've read about natural numbers, whole numbers, and integers in our previous classes. So now let's try and see how they are related to rational numbers. Natural numbers are all of these numbers are nothing but rational numbers with a denominator set to 1. Now let's try and see it pictorially. This smaller circle, which is representing n, is basically a set of natural numbers. The bigger circle, which is the light blue circle, this is basically representing all the whole numbers, and we all know that whole numbers is nothing but the natural numbers plus a number 0. So now if we see, the green circle is representing all the integers here. They are represented by z, and integers are again a superset of natural numbers and whole numbers because they contain the negative numbers as well. And now if we see the biggest circle, the dark blue color, which is represented by q, they actually represent the rational number. And now we'll try and see how it actually happens. As we've just explained, the natural numbers, whole numbers, and integers, if all of them are taken as quotients of integers with the denominator integer being 1, we can call that all of them are actually nothing but rational numbers. Now let's try and understand how are fractions related with the rational numbers. Fractions are also a subset of rational numbers because fractions are nothing but a part of a whole. So they're only positive, which would mean that they're actually the quotient of two whole numbers instead of the rational numbers, which are the quotient of two integers. So that means if we try and see it on the number line, we see that the right hand side of the number line, right hand side from 0 is basically representing the fractions, but the whole number line, all of these numbers which are represented on the number line are basically rational numbers. So we can say that rational numbers are basically a superset of the fractions. Now let's try and understand the decimal representation of rational numbers, because rational numbers we've defined till now as p by q, where both p and q are integers and q is not equal to 0. But can they be represented in any other form? Yes, rational numbers can also be represented in the decimal forms. So some of the terminating decimal numbers we'll take as an example, like 1.25. Now that's a terminating decimal number. What does terminating decimal number mean? Terminating decimal numbers are the numbers which have a decimal part, but the decimal part terminates after a fixed number of digits, and that fixed number of digit could be 2, could be 5, could be 10, could be 15, but it terminates at that point. So they're called the terminating decimal numbers. Now let's try and see, why do we say that the terminating decimal numbers are actually nothing but rational numbers? Let's try and convert these decimal numbers into the form p by q. So remove the simple part that we know is to remove the decimal and put an equivalent power of 10 in the denominator. Say for example, in the example that we've taken 1.25, if we remove the decimal, we put 100 in the denominator because there are two places after the decimal. So we simply make it 125 by 100, and then we try to simplify it to its simplest form by dividing it with a common factor, which is 25 in this case. So it becomes 5 by 4. Now we can clearly say that 5 by 4 is a rational number of the form p by q. So 1.25 is necessarily nothing but a rational number. So we can say that any such number, any terminating decimal numbers can be finally represented in the form of rational numbers. So they are rational numbers. Now we'll talk about another decimal representation of rational numbers, and that is non-terminating recurring decimal numbers. So we first talked about the terminating decimal numbers, where it terminates, it has a fixed number of digits after the decimal. But non-terminating recurring, what are the non-terminating recurring decimal numbers? These are the numbers which do not terminate after the decimal. Say for example, a number like 1.3333 and 33 continuing infinite number of times. That's a non-terminating recurring decimal number because it is not terminating. And why recurring? Because 3 is continuously repeated. So it's a recurring decimal number. And this number is of the form of pure recurring decimal number because the number after the decimal, the digit after the decimal, is completely repeated. That is the digit which is being repeated continuously. Then there are some numbers which are mixed recurring decimal, which is of the type 1.24, 535353. If we see in this part, 53 is the recurring part after the decimal, but 24 after the decimal are the digits which are not repeated. Right? So it is mixed recurring decimal. It is non-terminating for sure because 53 is continuing infinite number of times, but it is mixed in the sense that all the digits after the decimal are not recurring. Some digits occur only once and then they stop, and after that there are certain digits which continue to get repeated. So that pattern gets repeated over and over till infinite number of times. So that is why this is a mixed recurring decimal numbers. Now let's try and understand why these two type of non-terminating recurring decimal numbers are also a part of the rational numbers. Let's try and understand how do we convert these into the its p by q form. First of all, let's define a variable v x and make it equal to 1.3333. Now, if we multiply this by 10, the number becomes 10.3333, which clearly shows that the decimal part of the two numbers, which is x and 10x, remains the same. So now, since the decimal part remains the same, if we subtract these two, if we subtract first from the second, we'll clearly get a number which does not have a decimal part of it because the decimal part gets subtracted out. So if we subtract, we get 9x is equal to 12. So x is equal to 12 by 9. And simplifying it further, we get x is equal to 4 by 3. So the rational equivalent, rational p by q form of the number 1.33333 is 4 by 3. So we can clearly see that this number is also a rational number. So similarly, we can prove for the other one also that the non-terminating recurring decimal numbers are always rational numbers. Now, since we have said that all the numbers of the form p by q are rational numbers, we are saying the terminating decimal numbers and the non-terminating recurring decimal numbers are also rational numbers. So let's try and see, are there any numbers which do not fall under the category of rational numbers? Yes, there are quite a few. So first is the non-terminating, non-recurring decimal numbers. That's of the form 1.11, 01, 001, 0001. So if you see, none of the part after the decimal is recurring, right? If you see this part, it is different. Here it is 01, then 001, then 0001, and it is continuously changing. So none of the part as such is recurring. Now these cannot be represented in the form of p by q at all. So these are non-rational numbers. Then the numbers of the type which are not perfect square roots or cube roots, etc. For example, square root of 5, cube root of 9, and so on. These are not rational numbers because if we try to find the value till multiple decimal points, the decimals do not get repeated. So these are not rational numbers. And some mathematical constants like pi and e are also not rational numbers. Now, Now, it's important to understand, what is the use of rational numbers? Why are we studying rational numbers at all? Why can't we just, deal with whole numbers, integers? We were so happy dealing with whole numbers, integers, and natural numbers. Why are we introducing the concept of rational numbers here? So first of all, things around us do not always happen in integers. We know that, right? Sometimes we say we've done 1/8 of the task. We've had 1/6 of the pizza. So right, we don't eat the whole pizza in one go. We take piece by piece. So we say I've eaten 1/6 of the pizza. Similarly, now again, if we're talking about 1/8 of the task done, 1/6 of the pizza, then we're talking about fractions. Then why introduce the concept of rational numbers at all? If we already had fractions, we've studied them. So yes, in science, the vector quantities are there which need to be represented in negatives also. Hence the need for the negative rational number. So if we say that a car is moving from its point, if it moves in the left direction, then it's moving in a negative direction, and if it's moving in the right direction, it is moving in the positive direction. Now you cannot say that it has moved 5 meters without telling the direction, right? Supposing somebody is moving from his school to his home. Now you need to know the direction. If a person tries to take a direction opposite to the direction of his home, now he is farther away. If his school is 5 kilometers from home and he moves 1 kilometer from the school but in a direction opposite to the home, he'll be now 6 kilometers from home. But if he moves towards the home, he'll be 4 kilometers from home. So that clearly means that there is a concept of direction there, and that is where the numbers are represented, the quantities are represented with the negatives also. And due to the ease of calculations, some constants have been approximated to a rational number. That's another use of rational numbers. We just, in the previous slide, we just said that pi is not a rational number. But for simplicity in the calculations, pi is taken as 22/7 in many calculations. So that is where, there's another need. For the ease of calculations, we sometimes approximate the non-rational numbers, the irrational numbers, to the nearest rational number. Let's now try and understand some of the properties of rational number. First is the closure property. The properties are no different. You've studied all these properties in integers, in whole numbers, etc. So we'll study the same properties, but the properties may have a different, the property may be slightly different in case of rational numbers. The behavior of that property may be slightly different. So let's try and understand what is, first of all, the closure property. What is it? Closure property specifies that if the mentioned operation is performed on the rational number, the result is also a rational number. So closure property says that after any operation, after that particular operation is done on the rational numbers, the result will also be a rational number. So yes, if we see, for addition it is true, for subtraction it is true, for multiplication also it is true, but for division, if we say any rational number of the type a by b is divided by 0, and see, 0 is also a rational number because 0 has 0 in the numerator, not in the denominator. So 0 is a rational number. So if we divide any given number a by b by 0, the result is definitely not a rational number, because the rational number says that the denominator should not be 0. So the closure property of a rational number holds true for addition, subtraction, and multiplication, but does not hold true for division. Or we could say that rational numbers are not closed under division. Now, additive inverse. What does the additive inverse actually mean? Additive inverse is the number which when added to the same number results in a 0 as a result. So in case of a rational number, when a by b, we have to find the additive inverse of a by b. So clearly, if we add a minus a by b to a by b, the result would be 0. So minus a by b will be the additive inverse of a by b. Multiplicative inverse. What is multiplicative inverse? Multiplicative inverse is the number which, when multiplied by the given number, will result in a 1. So we can clearly say that a by b when multiplied by b by a will result in a 1. So b by a will be the multiplicative inverse of a by b. So we can say that the multiplicative inverse of any rational number would be its numerator and denominator switching places with each other. Moving on to some more properties of rational numbers. Let's talk about commutative property. Now, what is commutative property? Commutative property states that if you change the order of operation, if you reverse the order of operation, the result remains the same. So that means if you add a to b or you add b to a, the result would remain the same. Yes, it would remain the same in case of rational numbers also. But when we talk about subtraction, it is not the same. Let's take an example. Let's take one rational number is 1 by 5 and the other rational number is 1 by 8. If we subtract 1 by 8 from 1 by 5, the result is 3 by 40. While if we change the order and we subtract 1 by 5 from 1 by 8, the result would be minus 3 by 40, and clearly 3 by 40 and minus 3 by 40 are not the same rational numbers. So we can say that rational numbers do not hold the commutative property true for subtraction. It holds it for multiplication, but again, if we see it for division, a by b divided by c by d would not be equal to c by d divided by a by c. Let's take, for example, if we take two rational numbers 2 by 3 and 4 by 5, if I divide 2 by 3 by 4 by 5, the result is 10 by 12. But if I do other way around, if I divide 4 by 5 by 2 by 3, the result is 12 by 10. And again, we see that the results are not the same. So this means commutative property does not hold true for division of rational numbers. Okay, now let's move on to associative property. What does the associative property say? Associative property says that if we have an operation of the type A plus within brackets B plus C, this would be same as if we change the order of the operation by changing the brackets. If we make it in bracket A plus B and then plus C, it will remain the same. So yes, that holds true again for addition. But when we move to subtraction, A by B minus C by D minus E by F in bracket is not the same as subtracting C by D from A minus B and then subtracting E by F from the result. Let's see how. If we take three rational numbers here, 5 by 8 minus, then 1 by 4 minus 1 by 8 is in bracket. That is giving us 5 by 8 minus 1 by 8, which is 4 by 8 or 1 by 2. Now let's change the bracket and then see what happens. So if we subtract 1 by 4 from 5 by 8 first, then we get 3 by 8, and then we subtract 1 by 8 from 3 by 8, we get 2 by 8, which is 1 by 4. And 1 by 2 and 1 by 4 are not the same. So rational numbers are not associative under subtraction. And similarly, if we see that they are associative under multiplication, but under division, we again have the same issue. When we change the brackets, A by B divided by C by D divided by E by F, it is not equal to first dividing A by B by C by D and then dividing this result by E by F. We again take the same rational numbers and let's see what happens. If we do 5 by 8 divided by 1 by 4 divided by 1 by 8, we're getting 5 by 8 divided by 2, which is 5 by 16. But if we move the brackets to 5 by 8 divided by 1 by 4 first, we get a result of 5 by 2 and then divide by 1 by 8, which makes it 20. Now 5 by 16 and 20 are obviously not equal, so we can say that rational numbers are not associative under division. Continuing with the properties of rational numbers, what is additive identity? 0 is the additive identity of rational number. What is additive identity? Is any number which when added to a rational number does not change the rational number. So that clearly is 0. When you add 0 to any number, the number remains the same. So that is additive identity. Multiplicative identity is the number which, when multiplied with the given number, does not change the number. That clearly again is 1. If we multiply any given number with 1, the number does not change. So it's true for the rational numbers. Now let's talk about the distributive property of multiplication over addition and subtraction, which means a multiplied by, within brackets, b plus c is equal to a multiplied by b plus a multiplied by c. And for subtraction, it becomes a multiplied by b minus c is equal to a multiplied by b minus a multiplied by c, and that rational numbers hold this property true. Now let's try and understand some techniques for solving the questions related to rational numbers. Now, first thing while dealing with rational numbers is we should try and bring the rational number to its simplest form. And how do we do that is by dividing the numerator and denominator with a common factor so that we get the simplest form of the rational number. Then we use the properties of rational numbers to simplify them. The properties that we just talked about, the commutative property, associative property, distributive property, all these properties we use so that we can get a simplified rational number as a result. Now, if the expression to be solved is a mix of decimal and quotient form of rational numbers, then it is always advisable to change the decimal number to the quotient equivalent first and then simplify using the above two methods so that we get a final quotient form of rational number, which, if possible or if needed, can be converted to the decimal form also. Now let's move on to the quiz, some quizzes on the rational numbers. Now we've studied everything that we do with the rational numbers. Let's try and solve some of the questions. Can we find the square root of 0.00289 by 0.00144? And the options are given here. So let's try and solve them, and after we move on to all the quiz questions, we'll look at the solutions also. The second question is, let's try to simplify 32 by 6 multiplied by 0.3025 plus, then within brackets we have 16 by 3 multiplied by 1 by 100 plus 7 by 3. Now we need to use all those properties and other things that we've discussed to simplify this to get an answer which is true, which is one of these. And the third question on rational numbers is, convert this decimal 1.3585858 and so on to its PQ form. And again, this is of the type which is non-terminating, mixed, non-terminating recurring decimal number. So the choices are here, and we need to try and do it using the method that we talked about. Let's look at the solution for all these questions that we have given in the quiz. So we try to find out the square root of this number. We'll first convert the decimals to their P by Q equivalent, which would look like this, which make it 289 by 1 lakh divided by 144 divided by 1 lakh. So this is what we have to. So if we change the division to multiplication, and it becomes 289 by 1 lakh multiplied by 1 lakh by 144, which comes out to be finding a square root of 289 by 144. Now we know that the square root of 289 is 17 and the square root of 144 is 12. So the square root of P by Q is also equal to square root of P divided by square root of Q. So here is what we get as the answer. So option C is the correct answer. Let's look at the solution for question 2. Here we have a question again, we have a mixture of brackets, we have a mixture of decimal numbers plus the P by Q form of rational numbers. So first we'll change the decimal number to its P by Q form, and here is what we get. We try to simplify. We try to bring the rational number to its simplest form, which is bringing this number 3025 by 10,000 to its simplest form, which becomes 121 by 400, and also 32 by 6, bringing this to its simplest forms, gives us 16 by 3, and everything else was already in its simplest form. So now we use the associative property, which says that we can change the order of operation. We can move the brackets and we can change the order. This is true only for addition. So here that we are performing all the additions, we can use the associative property easily. And why do we actually do that? The reason is that we see a 16 by 3 as the common thing in both these terms. So now if we are trying to bring them together, we can take out 16 by 3 as the common factor and then simplify the remaining part of it. So that is the reason why we are trying to use the associative property here. So if we use the associative property and then bring out the common factor, which is 16 by 3 out, and then we get 16 by 3 multiplied by 121 by 400 plus 1 by 100, and this is basically using the distributive property over addition, and we keep 7 by 3 as it was. So now simplifying this, we get 16 by 3 multiplied by 125 by 400 plus 7 by 3. Now simplifying this, now we simplify because 125 by 400 is not in its simplest form, so we divide it by 25 and we get 5 by 16. So we get 16 by 3 multiplied by 5 by 16 plus 7 by 3, and this can further be simplified to 5 by 3 plus 7 by 3, which is equal to 12 by 3 and hence equal to 4. So in this case, option B is the correct answer. Now let's do the third question. Convert the decimal 1.3585858 to its p by q form. Now, as we had done in the presentation itself, in the video, in the previous part itself, let x be equal to 1.3585858, and then we say 10x is equal to 13.585858. Now if we see in the first and the second part, if we subtract first from the second, the decimal part of the two is not the same, so we'll still get something as the decimal part, so that would not be advisable. So now what do we do again here? So now if we see there are two decimal places which are getting repeated, we have 58 which is getting repeated here. So can we do one thing? We multiply this by 100 and we get 58 also on the left hand side of the decimal. So let's do that. We make it 1000x is equal to 1358.585858. Now if we see in these two terms, the decimal part is the same. Now we can subtract 2 from 3 to get 990x is equal to 1358.585858 minus 13.585858, which is equal to 1345, and x is equal to 1345 by 990. And of course we can, if the choices would have been like that, we could have further brought it into its simplest form, but since the options are like that, we say that option D is the correct answer. So friends, I'm sure you enjoyed learning the rational numbers. So have fun with them and keep doing a lot of practice on the rational numbers, and you'll start enjoying them as you understand and as you get comfortable with them. Keep posted on our channel for the new sessions which will keep coming, and you can also visit us at Cool Smart Learning website and Cool Smart Learning channel. Thank you.